Alright, so in this homework set we're going to learn a little bit about fracture mechanics. We're going to have a very quick and fast introduction to linear elastic fracture mechanics, or LEFM. We're talking about an analytical solution to stress fields. We're going to look at finite element results for the stress fields for a crack. And we're going to do a comparison between the analytical and finite element stress fields. And in particular, we're going to look at the Westergaard solution, which is for a biaxially loaded crack in a infinite plate. Now, some features of Abacus that we're going to learn about. We're going to deal a little bit with sets. We're going to learn how to write to the .dat file some specific nodal results. We're going to be able to save a query for a nodal output, and we're going to add commands to an input file and execute the input file from within CAE. So there's going to be some new features that we're going to learn about Abacus. My intention is that this will be the first of 3 lectures, videos on Abacus and fracture. The second one, I'd like to do some J-contour work and show you some input files that FEA-Crack can generate for us for looking at crack tip stress intensity factors. And then the third one, I hope to do some XFEM type work to show you an example of how cracks can be initiated based on failure criteria in the finite element model. So there should be some kind of fun things. So let's start with the quick introduction to linear elastic fracture mechanics. Alright, so what is fracture mechanics in general? Fracture mechanics is the study of bodies that contain cracks. Sounds simple enough. But we need to kind of talk about what a crack is and what it does for us. In continuum mechanics, which theory of elasticity is based on, we don't really like to talk about separation of bodies. Fracture mechanics kind of relaxes some of those tenets of fracture mechanics. In fracture mechanics, we like to think that we have a continuous body, but fracture mechanics, we can split that body, so a point that was unsplit before it starts to crack now goes into 2 different places. It may go in a positive direction and in the negative direction of our coordinate system as that crack starts to grow or propagate. So what do we mean by something that has a crack in it? Let me switch over to a different color. The easiest thing that we're going to start with is we just have maybe a plate, and it develops a crack in it. Maybe we're pulling on it in this direction, and this material starts to separate. If we were to exaggerate the deformation of that crack, it might take a shape something like this. And the idea then is that at this surface between the top surface and the bottom surface of this crack, we are not transmitting any stress. We don't have any tractions that go through that top and bottom surface anywhere along that crack front. And in fact, for the Westergaard solution, this was the basic idea, is that those surfaces needed to be traction free for stresses in the vertical direction and for stresses that are shear. Okay, so these go to 0 at that crack face. Now if you have a crack that closes, well then those surfaces can contact, and then you can transmit some stresses. Then the solution for the field would generally be like you had an uncracked body. What we're going to do in Abacus to start off with is just model a cracked plate, but we're going to look at a biaxially loaded plate, because that that goes along with our Westergaard solution. So what we're gonna look at is a situation where we have a cracked body and we have stresses that are in these two directions. So the far field stresses would be sigma x a long way away from the crack would be equal to sigma, and sigma y a long way away from the crack would be equal to sigma. All right, now I have a sequence of videos on the Westergaard solution. It requires a little bit of background in some math and some complex variables in particular, and theory of elasticity. If you would like to see that, that is available here. Let me back this up. There's actually 4 videos. Let's look at the playlist here. There's a sequence of 4 videos, basic math, review of elasticity, complex functions, and then we get into polar coordinates. And this 4th video really gets into the details of the Westergaard solution. And we're going to start with kind of the end point to all of this. When we get these stresses, sigma x, sigma y, and tau xy. Now if we wanted a uniaxially loaded plate, what we would do would be we would subtract off, we do a linear superposition, we just put a minus far field stress sigma on our sigma x term. And that's an interesting problem to do, but it makes the problem a little bit harder to solve analytically when we do our comparison. So that's why we're going to do the comparisons to the biaxially loaded plate. Now one of the things that we should talk about before we get too much further is this K1 term right here, this stress intensity factor, and what that is all about. So let's make a little bit of room and we'll get into those details. Let's compare and contrast failure conditions that we would learn in a class like mechanics and materials versus something that would account for small cracks within a body or fracture mechanics. So in mechanics and materials, we have a bar that's here, put some stress on it, and we know about the stress strain material, and our failure condition might be, okay, when this stress in our body gets to be greater than or equal to our ultimate stress, then the material fails. And we're quite happy applying that failure criterion as long as we don't get too concerned about small defects and cracks and things like that. But if you know that you have a crack in the body, then that's where things start to get a little bit more interesting. We can take the same bar and put a crack in it. And we know some about stress concentrations, but this is a little different. It's much more severe than a stress concentration. In fact, we get something called a stress intensity at the crack tip. Well, we know if we put a little bit of load on this, maybe this crack has a small size A, and a remote stress sigma applied to it. We know if we have a small stress and a small crack, we may not get a failure. We know if we have a large stress and a large crack, we probably will get a failure. But there's other conditions in between, maybe a medium-sized crack and a little bit of stress, or a fair amount of stress and a small crack. Those combinations could cause this thing to fracture. It's going to turn out that the way that we're going to characterize failure is if the stress intensity at the crack tip exceeds a material parameter called the critical stress intensity, or the fracture toughness. This is a material property. And it's determined by a compact tension specimen in the lab, or there's some other methods you can use. But the basic idea is you have a material, and you test it with a known crack length, and you see when the crack advances. It turns out that if you test thin materials and thick materials, there's a little bit of a difference. Thin materials tend to have kind of a high fracture toughness, and as you get to increase thickness, this value kind of stabilizes out to a particular value. So on this axis would be the thickness of the material, and this would be the KC value, and kind of dotted in here where this stabilizes out to a particular value at kind of thick pieces, we have what's called the plane strain fracture toughness, K1C. If you have thick bars, then it's this value. If you have thin materials, well, we're still going to use this value down here. That builds in a little bit of safety. Well, what is this K about? We'll talk about the subscript 1 in just a few moments. This K turns out to be a combination of stress and crack length. It comes about naturally through the Westergaard solution, but in a way we can kind of reason through it to some extent. Let's write down what it is, and then we'll talk about where it has come from. So if we go and analyze the Westergaard solution for the biaxially loaded cracked plate, and we go through the math, it'll turn out that if we look very near the crack tip in this very large plate, okay, we have the biaxial loading on it. Just going to draw a portion of this plate. That the stresses get very severe right here, and it turns out the stresses at the crack tip are in the form of the remote stress sigma times the square root of A. Okay, now A is the half length of the crack, 2A is the total length of the crack in the center cracked plate. Sigma square root A over the square root of 2, and I'll use the same notation that I used in my Westergaard video, the square root of X star. So this is on plane of Y equal to 0. So coming out ahead of this crack tip, where the distance from this point to the right is the distance X star, we have stresses that change by the square root of that distance. Now if you notice, that distance is to the 1/2 power, and it's on the bottom. As that distance gets really tiny, as it approaches 0, the stresses go to infinity. So we're going to expect to see a stress distribution, let me put it in a different color, that would be extremely high, tending to infinity right at x equals 0, and it tapers off by what's called a 1 over square root x, or 1 over square root r singularity. Okay, so the fact that we have this term on the bottom means that we have a singularity as we approach x star equal to 0. And this other term that is multiplying that 1 over square root x term is known as the strength of the singularity. Every crack problem in linear elastic fracture mechanics has, well, for mode 1 loading, and we'll talk about the modes later, has a very similar expression. It's 1 over the square root of this x or r distance. If you're in polar coordinates, you'd use r, times some stuff out in front of it. That stuff out in front is the strength of the singularity, and it's just dependent on the remote stress field, depending on the square root of the crack length, and it depends on some other coefficients that may be out in front of it. In this case, it's 1 over square root of 2. Sometimes you can have other effects like a finite width plate effect and things like that that you would add in as what's called a geometry factor. Well, the standard way to write this is, instead of using sigma square root A over square root 2 every time we write something down. So we're going to replace this, and we're going to equate K1, our stress intensity, and we're going to divide this by square root of 2 pi. We're going to set that equal to this sigma square root A over square root 2. And we can do a little bit of simplification to this. You know, the square root of 2's will cancel out. And we have a sigma square root A, and then we have a square root pi that we can bring over here. So K1 for a biaxially loaded cracked plate. This will also hold for a uniaxially loaded center cracked plate. It's going to be sigma times the square root of pi A. Okay, well, what does that do for us? Well, if we know our material property, K1C, one thing we can do is, if we're given a constant stress, we can solve this for a critical crack length. So at a certain stress level, what crack size do I need in order for this crack to propagate? Let's see if we square both sides and solve for AC. Let's see if I can do that. We'd have K1C squared over sigma squared, and then I'd have a pi, sigma squared, and then I'd have a pi on the bottom, it looks like. That would be my critical crack size. Another thing that we can do is, if we know that we have a fixed crack length, then I can find out what critical stress would cause this material to fracture. And so it's kind of an interesting thing. It's a combination of the stress and a parameter that has to do with the crack length that causes the crack to extend. So if you know you have a crack or a crack-like defect in your body, you have to be careful, and it's a combination of those two things. That's why in aircraft they monitor crack sizes. Once a crack reaches a certain length, then they pull that part out of service, and then they repair it or replace it, and then they start it over again, and they monitor the crack growth. You don't have to throw the part out if the crack is too small, but if it gets to a certain length, or before the next inspection interval, it would be anticipated to get to a critical length, then that component is pulled. All right, so that's kind of an interesting thing, and it's through the math, and it's not necessarily anything that we could have predicted without looking through the math. But the interesting thing is it has to do with the stress level and the square root of the crack length, or crack length parameter. So the K1C has some interesting units. It has units like megapascals, square root meters, or megapascals, square root millimeters, or KSI, square root inches. And whenever you look up K1C values, you have to be very careful in what unit system they're using for that, and you have to be careful when you convert from one unit system to another. Okay, so again, K1C is the fracture toughness, K1 is the stress intensity factor. So let's write that on here as well. So if we know we have a crack in our body, and if it's in tension, then all we need to do is figure out what the stress intensity factor is and plug it in, and we're good. We can find our critical crack size. The shape of the stress fields ahead of that crack tip are all very similar, except for the strength of the stress intensity, the K1 value. All right, let's talk a little bit next about mode 1, mode 2, and mode 3. All right, the people that established fracture mechanics have come up with 3 different modes of loading of cracks, and they call these mode 1, mode 2, and mode 3, and that's what the subscript on the K represents. So mode 1 is kind of pulling up and down And as you would normally tend to think of a crack, it opening up and propagating along this plane in front of this crack tip. And so we would look at what's called a mode 1 stress intensity factor. Mode 2 is a shear load, in plane shear, so maybe you're pushing this way and pulling that way on the crack. So we'd look at K2, stress intensity factor in mode 2. And mode 3, I guess I can finish this picture out. Mode 3 is what's known as anti-plane shear. And like you're pushing into the page down here and you're pulling out of the page this way. Now you could have mixed mode loading, which is a combination of modes 1, 2, and 3 as well. Now what we're going to focus on is mode 1. If you're in a fatigue situation, the crack is going to find a way to open in mode 1. It's going to align itself with the principal stresses in your body. It's going to propagate in a mode 1 type fashion, even if it might start out initiating as a mode 2 or a mode 3 or some other shear type initiation mechanism that you might have in your material. Chances are, if you're in a fatigue situation, it's going to somehow figure out a way to turn into a mode 1 situation. Like small cracks, maybe a little bit different. So mode 1 has been studied probably the most, and there's an extensive library of stress intensity factor solutions for all these different loading modes, but for mode 1 in particular. We can use numerical techniques to find stress intensities, and that's part of what we'll do probably in the second series of videos that I make on fracture mechanics with Abacus. Okay, but so I just wanted to label those modes. So if we go back and think about our Westergaard solution, we're opening the crack this way. Even though we have stresses applied this way, we are going to have a mode 1 type situation for our Westergaard solution. Alright, so let's write down those crack tip stress fields that we get from the Westergaard solution. Again, the details are all in those other videos, but here we have the stress fields for sigma x, sigma y, and tau xy. And you notice they have all a common term out in front of them, k1 over square root of 2 pi r, where r is radial distance from the crack tip. And again, these are near crack tip stress fields, so there was some analysis done to shrink the distance down, to be small with the distance compared to the crack length. And you notice it has a cosine theta over 2's in it. It's got some sine thetas over 2 and so forth. And what we're going to do, I'm going to show you how to do this. I'll probably just give you this Excel file. But we are going to take a look at the von Mises stress contours for this particular stress field. So let's refresh our memory on what the von Mises stress is. We have 1 over the square root of 2 sigma x minus sigma y squared plus sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 times each of the shearing stresses squared and that whole thing to the 1/2 power. And the reason why we're going to do this is because Abacus very easily spits out a von Mises stress contour for us. We'll be able to compare our stress contour from our analytical solution to the stress contours that we get from this analytical solution here, compare the final analytical solution. Now, for plane stress, which is the state of stress that we have for a thin plate, it's this center crack thin plate, a lot of these terms go away. Sigma z goes away, tau xz and tau yz goes away. And if you notice, the k1 over square root of 2 pi r is common to all of these. So if we want, let's see if we can do this, we're going to rewrite this as sigma von Mises squared. I'm going to square both sides. It's equal to 1 over 2 k1 squared over 2 pi r And the way I'm going to write this is we're going to have a function of theta for the x minus a function of theta for the y. We have a function of theta for x, function of theta for y, and then 6 times a function of x and y. These terms squared, and since I squared both sides, that's taken care of. Now I'm not going to write down these functions of theta there. There's these terms in these brackets. I need to close off those brackets there. But what we're going to do is for a given cracked geometry, we know our K1 is equal to sigma square root pi a. We're going to use 100 megapascals, and we're going to use 10 millimeters for the crack length. We can rearrange this formula and solve for a particular von Mises stress contour level. So if I flip this around, I'm going to solve for R. I'll go ahead and write this down just so I have it here. And we can solve for the value of R that lies on a contour. At any angle. So what I mean by that is we're going to start off with theta equal to 0, and we're going to solve for a value of R on a von Mises contour. Let's pick a number, 300 megapascals, with a remote stress of 100 megapascals, with a crack length of 10 millimeters. Okay, and then we're going to go maybe to 5 degrees. We're going to solve for the value of R that lies on that contour. And we're going to keep doing this all the way around from 0 to 360 degrees, and we're going to get some kind of stress contour that looks probably something kind of like that. Okay, so that's what our constant von Mises stress contour is. Now we can increase the von Mises contour or decrease it, and that would just give smaller or bigger contours, but the shape would be the same. So we're going to plug in different values of theta. We're going to compute the value of R, and then we're going to make a plot. So that's what I want to show you on my spreadsheet on the next page. Alright, so here's my spreadsheet, and I'll make this available to you. But let's take a look and let's make sure I have done everything right. We'll double check it. If you notice that I've made a mistake, if you watch this video, please let me know. So what I want to do is I want to go and sweep theta around the circle from 0 to 360 degrees. So I put that in there in degrees. Went every 2 degrees. So went down to 360 degrees to get me around the circle. And then I converted that into radians by multiplying by pi over 180. Now, these functions have theta over 2 and 3 theta over 2 in them. So here's theta over 2 in radians, and that should be 3 times theta over 2 in radians. And that should carry through on all these other columns. Okay, we need a cosine theta over 2. Okay, so that's the cosine of that column. We need a cosine of 3 theta over 2. So that's the cosine of that column. We need a sine of theta over 2. That's the sine of that column. We need a sine of 3 theta over 2, which is that one. Now my function of theta for x is cosine theta over 2 times the quantity 1 minus sine theta over 2 times sine 3 theta over 2. My theta functions for y is cosine theta over 2 times quantity 1 plus sine theta over 2 times sine 3 theta over 2. And my function for tau xy, my functions of theta for tau xy are sine theta over 2 times cosine theta over 2 times cosine 3 theta over 2. Here I set my von Mises contour level at 800. That's fine. You can change it. I said 300 here, but that's all right. My remote stress level is 100. My crack length, that's the half crack length, is going to be 10 millimeters. And my K1, which is sigma square root pi a for this geometry, let's just check that. Sigma times pi times the crack length to the 0.5 power. Okay, so that looks okay. Let me drag a partition over here. We need to find our R value. The way I did it was I first did this coefficient term right here. Let's check that out. So I have K1 squared, it's the blue box, divided by 2 pi times the von Mises stress level squared. And then I have the divided by 2. And that's the coefficient. And the Mises terms in here, I have the fx minus fy squared plus fx squared plus fy squared plus 6 times the fxy squared. So I think everything is okay. So when I put these together, I can solve for my value of R, which would be the coefficient and these Mises terms, that lies on my sigma von Mises contour level of 800 megapascals. Now I've converted that into x and y coordinates at the crack tip. X is equal to R cosine theta, y is equal to R sine theta. It's just a standard polar coordinate transformation. And now I'm shifting it to the plate center so it looks more like what we would see in our von Mises contour of our plate that we're going to build. Okay, and that's these values, the x shift. And so now I'm plotting the x shift versus the y. I'm plotting the xy components so I can use a standard Excel plotting function. That's what this plot is. So you see that the stress field is fairly flat out here. That's a function of the biaxial stress field. If we were to make this a uniaxial stress field, it would kind of curve in a little bit. It's kind of flat out here, and it approaches here, and it kind of curves in a little bit. Some people like to call this like a kidney bean shape stress contour. If we knew that our material yielded at a certain von Mises stress level, we can make this contour for the yielded material, and we can get an estimate of the yield zone ahead of the crack tip. So now let's stop this video, and for a part B, we'll get into the finite element part.